Hello everyone. I hope you can see the screen. So let's start our guest lecture. So today we have a very precious guest here, and he's going to talk about sketching algorithms. Let me introduce him briefly, and then I'll leave the virtual stage, to Dr. Jelani Nelson. Dr. Jelani Nelson is a professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. His research interests is in algorithm design analysis with focus on streaming algorithms, dimensionality reduction, compressed sensing, and randomized linear algebra algorithms. He completed his PhD in computer science at MIT in 2011, receiving the George M. Sprouse Award for Best Computer Science Doctoral Dissertation at MIT. He is the recipient of an NSF Career Award, ONR Young Investigator Award, Sloan Fellowship, and Presidential Early Career Award for Scientists and Engineers. A lot of, as you see, awards. In addition, in his earlier years, he frequently participated in programming competitions like AddisCoder, Google Collegium, and also served as a co-coach for MIT's ICPC team for 3 years while a PhD student, then for Harvard's team for several years as a faculty member. As you know, ICPC, just give me a second, let me. Okay, so let's see why. Okay, so as you know, ICPC is kind of the continuation of USA Computing Olympiad in the college. So, but it's a little bit different as a team and so on, but in terms of problems, you can say it's similar. By the way, so Dr. Jelani, we would like to welcome you all. I'm leaving the virtual stage to you right now. Okay, let me see if you have, so you can hear me now, right?
Yes, I can hear you. Can you hear me?
Yes, and then video, is there a problem with the video?
Yeah, when I try to start video, it says you cannot start your video because the host has stopped it. Maybe there's some setting to allow.
Oh yeah. Okay. So I'll leave it to you right now.
Okay.
So I think.
Oh, good. So now can you see me?
Yes, great. We can see you now. Okay, thank you.
Okay, well, thanks for inviting me, and let's get started with the talk.
Okay, I'm stopping to share my screen so I can read it to you.
Okay.
Great.
So I think this is working now. Can people see my slides?
Okay, we can see. Yes. Yeah.
Okay, great.
It seems it's working now.
Okay. And the way this is set up, can other people speak? Like if students have questions, or will they type their questions?
Okay, good question. This is a seminar. As far as I see, yeah, they can send messages as far as I know. So that's we can have Q&A session at the end too. So I can get them questions and so on. Yeah, they can send messages. Great.
Okay, so there's one part of the talk that's a little bit interactive, kind of in the middle. So maybe at that point, people can send their messages, and I'll pause to take a look. But I'll also, even in the middle, if people have questions, feel free to send them. I don't think I'll be able to see them in my screen sharing mode, but if they send them to you, feel free to interrupt me and tell me what the questions are. So I'm going to talk to you today about sketching algorithms. Okay, so what is sketching? So it's basically compressed data structures, so very low memory data structures. So you're given data, and you're given a set of possible queries Q that you might want to ask about that data. And a sketch is just a compressed representation of the data set that allows you to answer queries from that set of potential queries. And sometimes you want to answer queries that involve multiple data sets. So there's data set 1, which I have. There's data set 2, which you have. and we want to understand, maybe some different, query something about the difference of our data set or similarity across our data sets. And we want to do that just based on the sketches. So rather than me having to transmit all of my data to you or vice versa, we can just transmit the compressed representations to each other, and those compressed representations are enough to be able to answer queries. And streaming algorithms basically compress dynamic data structures, meaning that you want to maintain a sketch of the data as the data is being updated on the fly. Okay. Benefits of sketching, and I'll make this concrete soon with some examples. Benefits, it's compressed, I said, so the first benefit is less storage. Okay. It's faster, so since it's compressed, it doesn't need to fit on, say, disk, you can fit it in cache, okay, which means you can access it faster. And also reduce the amount of bandwidth needed for distributed computation. So imagine that there are many nodes in a network, in a computer network, that each have their data set, and they want to compute some function of the aggregate data set. Then because you only have to transmit sketches instead of entire data sets, you send less data over the wire, right? So you're using less bandwidth. So just so that we're all on the same page, I'm going to give you a really simple streaming example. So sketching where the data can be updated, which is the following. So, I'm an online vendor and people buy stuff from my website. I'm Amazon. I see a stream of transactions. Each transaction has a sales price. And there's only one query I'm interested in supporting, which is what were the gross sales for the day, the total sales? So this has a very simple solution, which is you just keep a running sum, one counter of memory, one word of memory. And when someone buys something new, you just add their sales price to your running sum. So this is extremely memory efficient. You only maintain one word of memory, and it's very fast to query. You just return what's in that word of memory. So the rest of the talk, I'm going to cover 3 examples that are not so simple. And these are the 3 that I'm going to cover. The first is approximate counting, then the heavy hitters problem or frequent items problem. Then I'll talk about graphs being updated in a data stream and wanting to maintain compressed representations of graphs. So let's start with approximate counting. Okay. So here's the problem I want to solve. And sorry if you hear my daughter crying in the background, sorry about that. So we want to run a simple data structure, which is just the counter, okay? So for example, we have a YouTube video, we want to keep track of how many people have seen the video or how many packets did my router route today, or et cetera. So here's the data structural problem. I want to maintain a counter C subject to 2 operations. One is query, which just returns what is the number that the counter represents. And the other is increment, which is just increment the counter by 1. And there's a very simple solution to this problem, which is just maintain a counter, okay? And if the number that you're representing grows to be k digits, you're going to use k units or k bits of memory to represent this counter. So the question is, can you do better? Is there a way I can somehow represent the number of increments so far using less than the number of digits needed to represent it? Can I store a k digit number in less than k units of memory? And the answer, of course, is no, by the pigeonhole principle, for those of you who've heard that term. But even though strictly speaking the answer is no, we're going to see that there is a meaningful way in that the answer actually is yes, that you can actually store a k digit number in less than k units of memory. And it's an algorithm due to Morris from the late 70s. This is Rob Morris. He was at Bell Labs, a research lab, an industrial research lab for 25 years, and then he became the chief scientist at the NSA. He's also father of another Rob Morris, the inventor of the first internet worm back in the late 80s. This is him, I think, on the day that he was about to go to court for his trial. He got arrested for spreading this worm. But all's well. I don't know if he actually served prison time, but he's now a professor at MIT in computer science. So he turned his life around. Okay. Anywho, so let me tell you about Morris's algorithm. So before I tell you his final algorithm, let me try and warm up to it and tell you some simpler ideas. So first of all, his algorithm is a randomized algorithm. I believe probably most, randomized algorithms are out of scope for example, USACO or the IOI. but they are, more broadly, randomization is a very, very useful tool in algorithm design. For example, if you've heard of quicksort, that's a randomized algorithm. So Morris's idea is, look, there's this number c that I'm trying to maintain, but what I'm going to store in memory is not actually going to be c. What I'm going to store in memory is a different number, x, initialized to 0. And whenever someone says increment, so they increment c, I'm not actually going to increment x. What I'm going to do is I'm going to flip a fair coin. If that coin comes up heads, then I'll increment x. If it comes up tails, then I won't do anything. I'll just leave x as it was. And what's the idea here? The idea here is, look, I only expect to increment x half the time, right? Because a fair coin comes up heads half the time. So kind of an expectation, this number x that I'm maintaining is going to be about c over 2. It's not probably going to be exactly c over 2 because there's some, variance here. This is a random process, but it's expected to be around c over 2. So I can still approximately tell you c. What I'll do is I'll just tell you 2 times x, right? Since x is roughly c over 2, if I tell you 2 times x, I'm roughly telling you c. So the downside, there's a pro and con to this. The pro is that basically instead of storing c, I'm storing c over 2, which is a smaller number. So since it's a smaller number, I'm saving like 1 digit of memory, right? The downside is that I'm only saving 1 digit of storage. And the other downside is that the error is terrible for small c. Okay, for example, if c is only 1, if someone only said increment once, then I'll either increment with probability 1/2, then x will be 1, or I won't increment with probability 1/2, which means x will be 0. So at the end of the day, when I return 2 times x, I'll either return 2 times 0 or 2 times 1. So I'll either return 0 or 2, even though the answer is 1. So I have no chance of telling you the right answer. And in fact, I'm guaranteed to be off from the truth by at least a factor of 2. I'm either going to say 0, which is off by an infinite multiplicative factor, or I'm going to say 2 when it's 1, and I'll be off by a factor of 2. This is not going to necessarily give me something that's within, say, 1% of the truth, right? I'd be happy if at least I could return to you a number that's within 1% of the truth with good probability. This is not giving me this. So first, let me tell you how to fix the first downside, which is I want to save much more than 1 digit. And then I'll talk about how to improve the error. So here's Morris's actual algorithm, or one version of it. Whenever the user says increment c, I'm not going to flip just 1 coin. I'm going to flip x coins. And then I'm going to increment x only if every single coin came up heads. Otherwise, I'll do nothing. So the probability that I increment x is 1 over 2 to the x. And it's possible to prove that in expectation, 2 to the x minus 1, you expect that to be c. Okay, it's possible to prove that mathematically. I'm not going to do it. So in other words, usually x is going to be about log c. Okay, so if a number needs k digits to write down, that means that the logarithm of that number only needs about log k digits to write down. So I've basically exponentially improved my memory. Instead of needing k digits, I only need approximately log k digits. Okay. There is that downside, though, still, that the error is terrible when c is small. And the fix to that is as follows. So if we increment x with probability 1 over 2 to the x, in other words, 0.5 to the x, then we save a lot of memory, but there's too much volatility. There's too much variance, especially when x is small. Okay, so we're not going to give a close answer with good probability. On the other hand, if we increment x with probability 1 to the x, instead of 0.5 to the x, 1 to the x, what are we actually doing? We're just maintaining a counter, right? 1 to the x means we're always incrementing. So we're just maintaining a counter. That's guaranteed to always output the right answer. But then our memory consumption isn't great. We're going to use k units of memory instead of log k. So on the one hand, so there's a trade-off, right? 0.5 to the x, we have very low memory but high variance. 1 to the x, we have very low memory, but we have very low variance, but high memory. So there's a trade-off between the variance and the memory. And as you might guess, there's a smooth trade-off here. So you could ask, why don't I do something in between? So what you can do is increment x with probability not 0.5 to the x and not 1 to the x, but 0.99 to the x. And you can prove that if you do this, then this expression, 1.01 to the x minus 1 times 100, in expectation is exactly c. It's the number you want. I'm not going to prove that for you here. And because you're almost always incrementing, you can prove that this estimator has low variance. You know, it's very concentrated around the right answer. So with good probability, you'll actually output the answer to within only 1% error. And altogether, if you want to have the right answer up to, say, a 1 plus epsilon factor, think of epsilon as 0.01, so 1% error, you can show that it's enough to use only log k plus log 1 over epsilon bits of memory. Basically, you're going to increment x with probability something like 1 minus epsilon squared to the x. That you need to mathematically analyze that and understand why that's the right thing, but it turns out that you can prove that. Okay, so this is an example of a streaming algorithm saving you an exponential amount of memory, but still giving you the right answer or close to the right answer with high probability. This is a randomized algorithm. Okay, so that's the first algorithm. And now I want to talk to you about two more algorithms. And this is the heavy hitters problem, also known as the frequent items problem. So what is the frequent items problem? Here's a fake search engine query log from some date. And if you're like me, when you want to find the Wikipedia page for something, you know, I don't pretty much never use Wikipedia's built-in search feature. I just Google wiki blah. So if I want to see the wiki page for Donald Trump, I Google wiki Trump. Okay, so wiki is very popular here. So basically what I want is an algorithm that sees these search queries coming in, okay? See, I put the times here. So they're coming in over some interval of time, starting from 6:58 p.m. to 7:11. So it sees them coming in. And then when you say query, it can tell you what's been popular recently. Like, oh, wait, a lot of people have been searching for wiki recently. So I want an algorithm that can do that and use very little memory. It doesn't have to remember everything it saw. So it's only keeping track of a sketch of what it saw. So formally, the problem is I'm given a stream of items. These items, for example, could be words coming from some universe U, which in this example is the dictionary. So I see a stream of words from the dictionary. These are search queries. And I want to report when someone says query, a list, a subset of the universe containing all the frequent words. Now, frequent depends on, what is the definition of frequent? I'll parameterize it by some integer k, positive integer k. And if the stream has L words in it, I'll say an item is k frequent if it appears strictly more than a 1 over k fraction of the time. Okay? So tell me all the words that appear strictly more than a 1 over k fraction of the time. An easy solution is just to maintain a histogram of length n. For every word that exists in the dictionary, just keep track how many times have I seen that word, right? You can answer then the frequent items queries, but you're using a lot of memory. So the question is there a way to use much less memory such that when someone says query, I can output a small list, a list that of size at most some constant times k, which is guaranteed to contain all the k frequent items. Notice that the number of k frequent items can never be more than k. In fact, it has to be strictly less than k, because if you're appearing more than 1 over k fraction of the time, there can be at most k of you, right? How many people can be, you know, how many candidates can have more than 10% of the vote? At most 10. Otherwise, it adds up to more than 100%, which is impossible, right? So this is the problem. And maybe now I'll just brief pause. Any questions, or feel free to type in your questions as I'm going. Fatih, let me know if you, from the view that I have right now, I actually can't see whether there are any questions when I screen share.
There are some questions actually.
Okay.
They ask, what about the compression?
Yeah, what about compression? Yeah, so
it was about, the k digits, storing k digits.
Yes.
So it can't store more than k digits in k digits. So that was, yeah.
Right. So the point is, we are compressing with that. With the approximate counting, we are compressing because normally to write C down, you need log C bits. We're not writing C down, we're writing X down. We only need log X bits. But X turns out to be very close to log C. So instead of storing log C, we're storing log X, which is log C. So the total number of bits we're writing down is doubly logarithmic. It's log instead of log. So that's a lot smaller. And how are we getting around? I told you it shouldn't be possible to store the number in less than k digits because you'll violate the pigeonhole principle. But the point is, we're not able to actually tell you the exact number. We're only able to tell you a number that's within 1% of the exact number. So if you settle for that kind of approximation, then you can actually get away with storing less in your memory. Okay. And were there any other questions? And maybe
there was a comment about time complexity of X. Your previous slides.
Yes.
And you're using, so it's the time complexity will be log X, isn't the time complexity will be log X or so?
So it depends on your model of computation. So the question is, how long does it take you to perform an update? So if you imagine that, if you call rand, right? Rand will give you not just a random bit, but it'll actually give you a random integer, right? So an int is, let's say, 32 bits. So it'll give you random 32 bits all at once. And if you're saying that I'm only going to increment if every single bit is heads, that's the same thing as saying I'll only increment, say, if every single bit is a 0. So you can just call rand and check whether rand is 0 or not. And if you want to just look at, r bits of the random number, you can just do a mask and only, basically mask it out so you're only getting the last r bits, and then check whether what you got is 0. So, if the numbers you're storing fit in a machine word, then it's basically one call to rand followed by a mask followed by checking equality with 0. So it's only 3 operations. It doesn't even need to grow with X, if that makes sense. Does that make sense? Basically, you can do it in constant time. You don't need to actually use log X time. Right, so I mean, another place where you see that, I mean, think about any algorithm where you need to index into an array, right? So you have an array of inputs like merge sort. You have an array of inputs and you want to sort them. Now, technically speaking, if that array has n elements in it, an index into the array is a number between 1 and n, which is log n bits. But you never say that indexing into an array takes log n time, right? Because that's not the model of the way your computer works, right? Your computer, you assume that indices into, that you assume that your word size of your machine, whether it be 32 bits or whether it be a 64-bit machine, the word size of your machine has enough bits that you can fit an index into memory in a single word, right? So you're assuming, you're already, even in classical algorithms like merge sort, et cetera, you're already implicitly making the assumption that you can manipulate kind of log n bits in constant time, right? Whether it be indexing into an array or whatever, or whether it be comparing two integers in an array, right? If you're sorting, you have to check, is X less than Y? If X is an int, it's 32 bits. Does it take you 32 time to check X less than Y? No, it takes constant time because that's how your machine is built. That's how your computer is built. It can do operations on machine words in constant time. Okay.
We have a couple questions here.
Yes.
Okay, so one of them is, why are we okay with the variance? Don't we want to prioritize with the accuracy first?
Don't we want to prioritize with what first, you say?
Accuracy.
Accuracy.
Yeah.
So first, I guess maybe you can tell me, Fatih, like, I guess, how is the students' backgrounds in, say, probability, like expectation, variance, things like that?
Okay, I can. So normally right now, in the audience, it's like from bronze level, you circle bronze to platinum level, from different levels.
Okay.
Some not much from probabilistic perspective. Some of them maybe Gold and above may know a lot about it. We have a lot of students from coming from having good math background, but may not be that much.
I see.
So,
okay. So I mean, so for all those listening, I mean, so variance actually relates to accuracy. So there's something called, say, Chebyshev's inequality, for example, or Bernstein's inequality. These are mathematical inequalities, probabilistic inequalities that tell you that if your random variable has low variance, then it will be very close to its expectation with good probability. So I'm not going to go into that in today's lecture, but if you want to look at this on your own, the key thing to search for is, for example, Chebyshev's inequality. That relates variance to accuracy. Okay. So maybe that's all I'll say about that. But yeah, it turns out variance is a useful thing to bound if you want to understand accuracy. Okay, good. So let me continue.
Actually, we have one more question.
Okay, yeah.
So the question is, can you package a number by doing something like taking it modulo, meaning large prime numbers that all systems know, and then for safety, an extra value that's coming like x minus x modulo n divided by n, where x is the number and n is the product of all those prime numbers.
Okay, so let me just back up. So the question is whether it's useful at all for this problem to store in memory x mod p for some prime p, maybe a random prime p. I don't know how that would be useful for this problem. Like one thing that is useful for is equality testing, right? So if I have two numbers, x and y, let's say I have x, you have y, and we want to test, is x equal to y or not? You know, if x and y are each k digits, I see Shreyas has a question. So if x and y are each k digits, then I could just send you x. That would be me telling you k digits. And then based on that, you can actually check whether or not x equals y. But, you know, is there a way for us to check whether our numbers are equal without sending k digits, maybe sending much less? And the answer is yes, you can actually get away with sending log k digits with a randomized approach. And it's exactly the approach that you said. You basically pick a random prime p, which is a log k digit number, okay? And then what I'll send you is I'll send you p as well as x mod p. And then you'll check whether or not y mod p is equal to x mod p. And you'll say that they're equal if and only if they're equal mod p. And basically the reason this works is, right, x is equal to y mod p if and only if x minus y is divisible by p, right? But if x minus y is a k-digit number, then you can prove that the number of prime divisors it has is at most something like k over log k. This is, I mean, this follows by a calculation. So as long as you pick a random prime that's big enough, it's unlikely that the random prime you pick will be one of the divisors. This follows by something called the prime number theorem. You need to know that there are enough primes such that, you know, the divisor is unlikely to be one of the ones you pick. But I don't know how to use that prime trick for this particular problem of just approximate counting. But it is useful for equality testing. And maybe I'll take those. So Shreyas had a question as well.
Another question, yeah. If the number is big enough, could you layer these operations on top of each other a bunch of times?
If the number is big enough, could you layer these operations on top of each other? You mean to compress the compression? Is that the question?
Okay, yeah. So Larry, can you tell it, please?
I mean, for one thing I'll say is that there's a lower bound. If all you're promised is that the number is at most n, you actually need log n bits of memory. So there's nothing clever you can do, compress the compression, whatever. There's nothing you can do to get better because log n is actually optimal up to a constant factor. So maybe that answers that question.
Another question.
Yes.
If C is so large that we have to use the discuss algorithm to store it with x.
Yeah.
Won't calculating the estimated value of x become an issue since if computers can't handle it, calculators, humans won't be able to find it either.
Yeah. So in a lot of these, so that's a good question. The question is like, okay, you're storing this compressed representation, but at the end of the day, when someone finally says query and you have to actually tell me C, then that C that you're telling me is a really big number. So I'm gonna have to expand and use a lot of memory anyway. So there are a few answers to that. One answer is, depending on what you want, I don't necessarily have to tell you C. I can just tell you enough that you can go off and later recover an approximate C on your own. So I can basically just tell you X, right? And then you know how to get C from X. So you can do that yourself. You don't need me to do it for you. Another thing too is, like in a lot of these applications where people use sketching and streaming algorithms, they're not just running one such algorithm, by itself. They're running lots of sketching algorithms simultaneously, and basically, it's you want them each to be small so that in aggregate the total memory you're using is small. But if at any given point in time you want to query just like one of them, you don't mind necessarily using a little more space to get the answer for that one. You just don't want to use a lot of space for all of them simultaneously. So yeah, so maybe because I have a lot, I realize I'm already half an hour in and I have a lot more to tell you about. So maybe let's pause on the questions for now, and then I'll come back to ask questions after we do frequent items. Okay. So let's continue. So I already told you about this problem where I want to notice that wiki is popular. So here's a related problem called change detection. So there's the search queries from yesterday and there's the search queries from today. Now wiki is actually popular both days. So because it's popular both days, maybe I think that's not interesting, right? I want to know kind of what's changing in the world. So I want to know what are the things that weren't popular yesterday but are today, or vice versa. What are the things that changed a lot? So for example, the word prime all of a sudden became popular. And why did that happen on July 16, 2018? Because I don't know if people remember, there was Amazon Prime Day on July 16, 2018, where a lot of things on Amazon were on sale. Okay, and so there were so many people trying to search for things on Amazon to buy at a discount that day that Amazon.com actually crashed. So this is actually me. This is a screenshot of me trying to search for something on Amazon.com on July 18th and getting this puppy face. Okay, and there were articles about Amazon crashing because of Prime Day. So I would like to notice. Right, I'm some data analyst. I want to notice this happening in real time. Like, oh, a lot of people are searching for Prime. Okay, and then I can dig into why that might be happening. Okay, so this change detection is related to frequent items because basically kind of what are the big frequencies in the difference vector between today and yesterday. So this motivates a model called the turnstile streaming model, where you have some high dimensional vector x that starts as the 0 vector. So for example, n might be the dictionary. It's indexed by words in the dictionary. So x is basically a histogram of all the words. And you see a sequence of updates where each update adds some amount to some entry in x. For example, delta is always 1. So when I see word I increment the ith entry in the histogram. And then someone has some query they'd like to ask, which is, they want to query some function of this histogram. And I want to use very little memory. I don't want to store the histogram in memory. I want to use much less than linear memory. And there are lots of different things that people ask about in this model, like the number of support size of x, so the number of non-zero entries in x. In other words, what's the number of distinct words that people have searched for today? Okay. Point query. They want to know what is xi. So how many times did people search for prime? Or frequent. They want to have a small list containing all the frequent words. Okay. And let me actually maybe skip this. Okay, but and let me say that there have been a lot of works on heavy hitters on frequent items. I'm not going to talk about all of them today. I'm going to just talk about the two oldest ones. Some of the more recent ones I was involved in. You can see expander sketch, the n period is me, or the BP tree, the n period is me. But I'm going to talk about some older algorithms that are easier to explain. Okay. And I'm going to focus on the insertion only model, which means that basically people are allowed to see words, but they're not allowed to delete words. In the turnstile model, so maybe I should go back. So the insertion only model means that delta is always 1. They're always adding 1 to some entry in the histogram. That's the first example where I wanted to notice that wiki was popular. Strict turnstile, we're going to talk about a little bit later. People are allowed to insert word items and also delete items, but they can never delete what they haven't already inserted. So every entry in the histogram is always non-negative. So for example, I have a graph on n vertices. Okay, so the dimension of the histogram is n choose 2, basically all the possible edges that could be in the graph. So when someone inserts an edge, they're adding 1 to one of these n choose 2 entries. When someone deletes an edge in the graph, they're deleting 1 from one of these entries in the histogram. So for example, in a dynamic graph, people are becoming friends on Facebook. So you insert an edge, people unfriend each other on Facebook. So you're deleting an edge. But you can never unfriend someone if they were not already your friend. So you're never going to delete an edge that wasn't already there. So that would be the strict turnstile model. The general turnstile model means you're allowed to delete things even if you never saw them. So for example, with change detection, where I want to notice that something became popular and it wasn't popular before, or vice versa, you can imagine that all the words I saw yesterday, delta is +1. All the words I saw today, delta is -1. So what is xi at the end of both days? It's the difference between yesterday and today. So the difference could be positive, it could be negative, because I might have seen it more yesterday, I might have seen it more today. But that's the general turnstile model. Okay. So some of these algorithms that I wrote on this slide, they only work in strict turnstile, but not general, or they work in general turnstile, or they only work in insertion only, or they're deterministic, but they use more memory, or they're probabilistic, but they use less memory. So there are all kinds of trade-offs, and I'm not going to talk about all of them, but I will talk about these two, sampling and frequent. And those are both algorithms that work in the insertion only model. And first, let's talk about sampling. And the sampling algorithm is very easy to understand, why it works. There's some, if you want to analyze it rigorously, you need to use something like Chebyshev's inequality or the Chernoff bound, but just the idea of it is simple. So the idea is, look, if a word is being searched for a lot, like people are searching for wiki 10% of the time, then if you don't remember the entire stream of words, but you just randomly sample the stream and you only remember a very small fraction of the stuff you saw, then stuff that was popular should show up in your very small fraction. This is already the concept behind polling, right? So I want to know what fraction of people are going to vote for Biden in the national election versus Trump, okay? There are, maybe, I don't know how many people are registered voters in America, but it's over 100 million, I imagine. There are a lot of people who vote in America. Now, the way people run polls is they don't call every adult in America and ask them, who are you voting for? That would be very inefficient. That's how you run the election, right? But the way you run a poll is you just sample. You just call maybe 1,000 people and random people, and you ask them, who are you voting for? And the point is, if one of the candidates has an overwhelming majority of the vote, that's going to show up in your sample, right? If 70% of the people are deciding they want to vote for Biden, then close to 70% of a random sample will also vote for Biden, or vice versa, right? So that's the idea behind sampling, and that's the idea behind this algorithm. You just sample, and you look at what are the frequent words in the sample, okay? And kind of mathematically, you can show that if each word you keep with probability k squared log n over L, where L is the length of the stream, it's possible to show via something called the Chernoff-Hufting bound that each item's relative frequency in the sample will be roughly what it is in reality. So if you just return what's frequent in the sample, that's enough, okay? And basically you only expect to store something like k squared log n items if you do this. Okay. Now there's another algorithm which is frequent, which is better. It's strictly better in every single way imaginable. It uses less memory and it's deterministic. So it's guaranteed to always give the right answer. And the frequent algorithm comes from the majority algorithm, which is from 1981. It was invented by Boyer and Moore. And it solves the case when k equals 2. So if some item in the stream appears a strict majority of the time, their algorithm is guaranteed to find it. And I'm going to tell you what their algorithm is by running it on an example, and then it'll be clear how it operates. I'm not going to prove that it works, but I'll leave that to you as an exercise. So what is the algorithm? So the algorithm keeps track of only two things. One is the candidate item, who I currently think is the majority item. And the second thing is a count, which is the number of times. It's going to be something like the number of times I've seen this item. It's going to be an underestimate of that. Initially, I haven't seen anything, so I have no candidate item. It's null. Then I go through the stream of words one by one. So I see Canada. Okay. Since I have no candidate, I'll just say that Canada is now my candidate. And I've seen it once. Now I've seen Canada again. So now I've seen it twice. Now I see toys. Toys does not match my candidate. So what the algorithm does is it decrements one from the candidate, from the count, and it moves on. Then it sees R. R does not match my candidate, so I decrement one from the count. Now my count is 0. So whenever the count is 0, I replace the candidate with the word I just saw, and I set the count to be 1. Now I see us. Us doesn't match the candidate. I decrement to 0. Oh, the count is 0. I'll replace the candidate with the new word. And then the same thing again. Canada doesn't match the candidate. I decrement. I replace the candidate with Canada. And voila, the stream is over. I'll return the candidate, which is Canada. Okay. So you can prove, I won't do it today, but you can prove that whatever word is the strict majority, if there is one strict majority, it'll return it. Okay. So Mishra and Grease, just a year later, showed how to generalize this to the case when a word appears strictly more than a 1/k fraction of the time. Their algorithm is guaranteed to find it. Okay, so what does their thing do, their algorithm? It doesn't keep track of just one candidate. It keeps track of k-1 candidates. Okay? And then now, whenever you see a word in the stream, if that word matches any of the candidates, you increment the counter of that candidate. Otherwise, if it doesn't match any of the candidates, you decrement every single counter by 1. And then if any of the counters become 0, you just throw away that item and then you replace it with the new item you just saw. If multiple of them become 0, then all the other ones you can replace them with null. And one of them you replace with the word you just saw. Okay? So that's their algorithm. And when someone says query, you just return the list of all the candidates that you're storing. And it's possible to prove that what you return is guaranteed to contain every item that appears strictly more than a 1/k fraction of the time. Okay, so that's the Mishra-Grease algorithm. So that's that. And before I move on to the third algorithm, let me open it up again for questions. Any questions?
There was one question which says, what if there is a surge that takes place during your sample, when you're doing sampling?
What if there's a
surge?
Yeah, so
I
guess the model I'm assuming here is something like dynamic data structures. So there are updates and queries. So an update is like I see a new word. So when someone says query, kind of time freezes and you just have to return what's frequent up until that query time. So any searches to your search engine that happened after they said query are not counted. If you query again later in the future, then it will be counted. But the query will only, your answer will only respond to things up to that query point. Does that make sense? Okay. Okay, so let me continue then. I want to do the third thing. Oh, yes, question?
Yeah, I think it's okay.
Okay.
So no more questions. We
Okay.
don't have any questions.
So now this one is going to be a little interactive. And after I talk about this stuff, I wanted to change gears a little bit and talk about something else related to algorithms. So imagine now you have a huge graph like Facebook. There are like 1 billion people on Facebook, okay? But the graph is dynamically changing, like people are becoming friends, unfriending each other, etc. So we have a large streaming graph. But before I talk about that, let's play a game together. And here's the game. I am holding, I say you, but I am holding a basket of fruit. This basket initially is empty. At every time step, you can do one of two things. You can either take a fruit and put it in my basket. So let's say you take an apple, you put it in my basket. or you can look in the basket and take anything out that you'd like, okay? You can also put multiple of the same fruit in my basket. You can put 3 oranges in my basket if you want to. Okay? Now, I get to see the items as you put them in and remove them. I can see that you put an apple. I can see that you took out an orange, but I don't allow myself to ever look in the basket, okay? So in principle, I should know what's in the basket because I'm seeing everything that's happening. In reality, I'm a human with bounded memory, okay? So I might start forgetting stuff. So the question is, using bounded memory, is it possible to do the following? When you say query, I need to report to you one fruit that's still in the basket. I don't even need to tell you everything that's in the basket. I just need to tell you one thing that's in the basket, okay? So before we start trying to answer questions about graphs, imagine there's a huge graph on n vertices. There are n choose 2 possible edges. In other words, n choose 2 possible fruits, okay? Each edge is a fruit. Before I can answer questions like, you know, find me a path from S to T or find the shortest path or whatever, here's an even simpler problem. Just tell me any edge that's still in the graph. That's non-trivial, right? Because if you try to remember an edge, like I might later delete that edge. And then, you know, you haven't been keeping track of all the edges. So what are the other edges that are still in the graph? You don't know. So this is a non-trivial problem. So let's play the game together. Now the basket is empty and you just inserted a strawberry. Now you inserted a watermelon, then a grape, then an orange, then a peach, then a banana, then another peach. So now there are 2 peaches in the basket, but you removed one, so there's only 1 peach left in the basket. You inserted a mango, but then you removed the second peach. So now there are no peaches in the basket. You insert a pineapple, an apple, a cherry, a blueberry, a raspberry, a pear, a plum, a blackberry, a kiwi, a honeydew, a tangerine, a lemon, a pomegranate, an apricot, nectarine, avocado, cantaloupe, coconut, grapefruit, lime, lychee, fig, papaya, passion fruit, and now you start removing things. Now you reach in the basket and you remove a fig. You remove a kiwi, an avocado, a banana, a raspberry, honeydew, blueberry, apricot, blackberry, watermelon, grapefruit, passion fruit, strawberry, lemon, mango, coconut, orange, apple, nectarine, tangerine, cantaloupe, papaya, lychee, pomegranate, grape, cherry, pineapple, pear, query.
Oh, it's hard.
So now I promise you that there are 2 fruits that are still in this basket. So I want you to tell me, just name one fruit. What's one fruit that's still in this basket? So I'm going to stop sharing for a second so I can see what people are typing.
Okay, I made it public. The people are typing it publicly so everybody can see their answers. Or I can make it.
Okay, good. So I see passion fruit. No, passion fruit is still in the basket. Any other guesses? Durian was never in there. Apple, nope. Watermelon, nope. Pineapple, nope. I removed all of those. Honeydew, I removed the honeydew. I'm sorry. I can show you proof. I can go back to the slide. It's not a trick question. There are two things I inserted that I never removed.
Coconut?
It's not tangerine or lemon. It's not cantaloupe. Nope. So I'll take just three more guesses. Strawberry, no, I removed the strawberry. I removed the apple. One more. Banana. Nope, I removed the banana.
Coconut.
Nope.
Coconut. No.
Sorry, I removed the coconut. So I'll tell you now what's left. And it's amazing because, you know, if everybody just kind of guessed a random thing, you would think that someone would hit it, right? But no, everybody got it wrong. Okay. So there are 2 things left, and it's plum and lime. So, you know, if you want to make sure I'm not cheating, I can share the slides with Fatih. You can look over them. But there's still a plum and a lime in this basket. So, you know, you can see it's not that trivial. And here's the problem, right? Basically, maintain a histogram in the turnstile streaming model such that when someone says query, just report any I such that zi is not 0. Report anything that hasn't been deleted yet. And in 2012, Guha and McGregor showed that if you have a data structure that solves this problem, you can actually use it as a subroutine to solve dynamic spanning forest using only v log cubed v bits of memory, where v is the number of vertices in a graph, okay? So if you think about it, this is non-trivial, right? Because if there's a graph on v vertices, naively, you would need v choose 2, roughly v squared bits of memory to remember which edges are there and not there, okay? but you don't actually need v squared. You can actually use v log cubed v. Now, again, if there are no deletions of edges, this is also very easy. If no one ever deletes an edge, how do I maintain a spanning forest? I can just use, for example, a union find data structure, right? Whenever someone inserts an edge, if it connects to connected components that weren't connected before, I remember the edge. If it connects two vertices that are already in the same connected component, I can just ignore the edge because they're already connected anyway. I don't need to remember this edge. Okay. The problem is when you allow deletion of edges, then it's non-trivial, because if I'm trying to remember a spanning forest, what if someone deletes one of the edges in my forest? There might be a replacement edge that still connects those two components, but since I'm not remembering everything, I might not know that there's a replacement edge. But what they show is the surprising result that actually there's a randomized algorithm that only needs v log cubed v bits of memory, and it works by using this solution to the fruit game as a subroutine. It uses lots of solutions to the fruit game as subroutines. Okay. And in fact, there's a data structure for the fruit game that succeeds with probability delta, with 1 minus delta. In other words, it'll say a wrong answer with probability delta, but it'll tell you a correct fruit with probability 1 minus delta. And the amount of memory it uses is log 1 over delta times log squared n bits, where n is the number of fruits that exist in the universe. And there are even versions of this that work for sampling. So they don't just tell you, for example, they don't just tell you a fruit that's still in the basket, but they can even tell you a uniformly random fruit that's still in the basket, or random where you bias yourself toward fruits that there are more of in the basket. You know, there are all kinds of things you can do, but basically this is solvable. And in fact, you can actually use the fruit game subroutine to solve lots of other things in small memory, like connectivity, k-connectivity, minimum spanning tree, max matching, vertex cover, et cetera, densest subgraph. So it looks just like a game, but in fact, this game has real applications. Okay. And a theorem that I have, so this is joint work with other people, is that the algorithm of Johari, Saglam, and Tardosh from 2011 actually is optimal. So what we showed is that you actually, the memory that they use in their algorithm, there actually is no algorithm that uses less memory than that by more than a constant factor. And I'm not going to be able to tell you about this today, like how to prove it. And I'm not going to go into how the algorithm works. It uses a bit of linear algebra, which I'm not going to get into today. But maybe in the Q&A session, if we have time, I can entertain such questions. And maybe I'll skip this for now. So let me skip all this stuff. It's a bit technical. Okay. And let me change gears for the last few minutes of the talk. So I'm a professor. What do professors do? We do research, okay, but we also teach courses. And I personally happen to love teaching. And I would say that even aside from my job, I also consider teaching to be my hobby. And I teach even beyond what the job requires. And here's an example of something that I teach. So you are here part of a summer camp on algorithms or math or what have you. I also run a summer camp, not this summer, unfortunately, due to COVID, but I run a summer camp most summers called AddisCoder. And it's a 4-week course that I run in Addis Ababa, which is the capital of Ethiopia. It runs in Ethiopia. And we cover kind of basic programming and then algorithms. And I'll say a little bit more. And so far, we've had more than 500 students complete this course. So here are some of the alumni from the program over 4 years. So in the beginning, we had this big gap between 2011 and 2016 when I didn't run the course because I was really busy with starting a new job at Harvard. But nowadays, we basically run the course every summer. So we have very smart students. We've had like 4 of them go straight from Ethiopia, from high school to to MIT, several to Princeton, to Harvard, to Brown, et cetera. One of them is actually in the Bay Area with you all. He's at Stanford. He just finished his freshman year. That's Haile Mikhail in the 3rd column, 2nd row, 3rd column. And in fact, the second, 1st column, 2nd row, Shalom, when he entered MIT, he actually was a teaching assistant for the main algorithms course at MIT 5 times. And he won a teaching award for teaching algorithms at MIT. So he loved algorithms so much that he decided to stick with it. He ended up doing a master's thesis on quantum computing, and now he's working at Google. And several others from the older batches are now doing PhDs in math, computer science, mechanical engineering, et cetera. So why am I telling you about this? And I repeated it several times, once in the US Virgin Islands, which is actually where I grew up, but several times in Ethiopia. And how did it get started, and why am I telling you about this? So, you know, like you all maybe, when I was young, first of all, I didn't know what an algorithm was when I was in high school. I just, you know, I wasn't exposed to it. So you all are very lucky that you're finding out about this great stuff in your youth. I found out about algorithms when I was in college. You know, I went to MIT for college, and there were a lot of people there who did IOI, for example, or IMO. So just kind of from knowing them, I learned about competitive programming myself, and I kind of self-trained when I was in college, doing a lot of online judge problems and top coder problems, et cetera. So back in college, you know, and maybe you, now that you all are just first starting to learn about this kind of stuff, I was really, you know, I got really hooked by this, to me, it was like a game. I got really hooked by this game of competitive programming. And I spent, you know, there was one summer after junior year of undergrad where I spent like 8 hours a day just training myself on online judge problems. But then over the years, you know, I liked kind of getting better and better at it and learning more stuff. But later, as I got older, you know, I was inspired by something that I saw. It inspired me to kind of think outside of myself for a little bit. And I'm telling you about this to hopefully maybe inspire you in your future. So basically, you know, I was learning a bunch of stuff about competitive programming. I was doing internships. I interned at Google. I interned at Toshiba. I was doing research. And then I learned about this thing, MIT Global Startup Lab. It's back then, that's what it's known as now. Back when it first started, it was known as the Africa IT Initiative. It was actually created by undergrads at MIT, international students, 2 from Kenya and 1 from Ethiopia, international undergrads. And they basically founded a summer program that taught not only kind of computer science skills, but also entrepreneurship. So they had like a summer camp where college students in their respective countries would learn all this, you know, stuff, CS stuff over the summer, but they would have a project in mind. And at the end of the summer, they would try to turn their projects into companies. Okay. And it impacted more than about 500 local students and teachers in Kenya, Ethiopia, and Ghana. And there were about 30 MIT students who served as volunteers for this program. So my program is a high school program. It's an algorithms camp. It has nothing to do with entrepreneurship, but they just kind of inspired me because, you know, the idea of service, you know, I guess it's not that I didn't value community service. It's that I just never really thought about doing it. I was so busy with my homeworks and my training myself in competitive programming, et cetera, that I never really thought about kind of the broader world. Okay. So when I saw this program that these 3 created, Paul, Martin, and Solomon, who are from Kenya, and Ethiopia, it kind of inspired me. So, and now their program is actually, it's not just an undergrad club anymore. It was overtaken by MIT. It's a regular part of MIT now. It's renamed the Global Startup Lab. And they're not only in Africa, they're in Sri Lanka, they're kind of all over the world now. And it's become a really big thing that runs every year. Okay. So I'm just telling you about this to maybe inspire you or put the seed in your head so that maybe one day you'll think, maybe I'll do, it doesn't have to be, you don't have to go and teach in Ethiopia. I mean, the reason I did that is because I'm personally half Ethiopian. I was visiting relatives and I thought, why don't I teach a course while I'm there? And the idea to teach a course came from, you know, the AITI, seeing AITI. But, you know, think about other things in your community and you know, things that you might want to do. And I hope that I'm planting the seed in your head to do so. So more on AddisCoder. The very first, you know, the second offering we had about more than 80 students, almost half were women, were girls. We had students from every region of Ethiopia, so every state basically. Many of the students had never used a computer before. So Ethiopia is, you know, it's a country where the majority of the population, about 80%, live in rural areas, and you know, basically are, you know, live in they're in families that farm. Okay, so there are many students amongst these 82 who hadn't even used a computer before. We actually had to give a crash course one weekend on like basic computer skills, like right-clicking with a mouse. Class was pretty intense. It was 8 to 9 hours a day, 5 days a week for a month. Mostly lab exercises where we're having them solve problems, but we had about an hour and a half to 2 hours of lecture each day. So we started off with the absolute basics, like what is a variable? Like what is, you know, basics of Python? What is a function? And then we started doing problem solving, recursion, Gaussian elimination, and more algorithms, sorting, merge sort, binary search, hashing, dynamic programming, Karatsuba's algorithm for fast integer multiplication, Bellman-Ford, Floyd-Warshall, etc. And I actually co-organized this with an organization, a nonprofit in Ethiopia, founded by the family of the late prime minister. And we ended up actually working with the government, with the Ministry of Education, and they helped us select top students from all over the country and bring them to the capital, give them dorms, room and board, give them cafeteria food to participate in the program. Great, so that was also pretty exciting that it expanded to include basically everyone from the country. Ethiopia, by the way, is a big country. It's the second most populous country in Africa after Nigeria. The population of Ethiopia is about 110 million, okay? So it's like a third of America, of the US. It's quite big. And then in 2018 and 2019, we basically doubled the size of the program to 175 students. Here's a survey from last summer. Basically, if you look in the left column, we asked students, what did you want to major in before our program? In the right column, it's what did you want to major in after our program? And basically the number of students who switched into computer science tripled, okay? So CS is not a part of the standard curriculum in Ethiopia for high school. So a lot of kids didn't even really know what CS was all about. People of course have heard of computers, but what does it mean to have a career in computer science or to major in computer science? People had no idea. So after being exposed to algorithms and programming, a lot of the kids got interested. And in fact, several of the former students and TAs, including the one who's at Stanford right now, created spin-off programs that run in other cities based on our syllabus. So let me just show you some pictures. So this is actually the program in action. These are three girls, Zakira and Iskadad. This was the program in 2016. If you see in the back, there's a boy looking down with a blue shirt. He's actually at MIT right now. He just finished his sophomore year. His name is Jonathan. These are TAs for the program, 4 TAs. I think Brian Gu, he's on the right side. He might have actually been a TA for your program, Fatih, is that right? Or?
He was a teacher before in AlphaStar, yeah.
Okay, so you can.
And also Joanne. I see Joanne
really?
here.
Joanne too. Okay, yeah. So two of them were. So Joanne is the first woman on the left sitting down, and then on the right you can see the guy looking at his phone. That's Brian. He was also a TA for AlphaStar. And then the other two, Kudus graduated from Harvard, now is a PhD student at University of Michigan in statistics. And Emily did her undergrad at MIT, now she's a PhD student at MIT. So I'm not the only instructor. Boaz Barak, he's a professor at Harvard, came in, taught he's a regular instructor for the program. Mikhail with the hoodie here, he actually is an alumnus from the program, and then he graduated from Princeton, and now he's working at Google in the Bay Area. So he's actually local, he's in the Bay Area as well. This is several girls who did the program in 2016. This is 2018 people. In the middle, Sahana with the green pants. She's a PhD student at Stanford. She volunteered as a TA for the program one summer. This is the program last summer. This was the graduation. They're all wearing purple shirts that say AddisCoder. And then this is all the teaching staff from last summer. So some of these people actually did competitive programming. Like, I don't know if you can see in the back row, the second guy from the left, he's actually, so our TAs actually are from all over the world. We allow anyone to apply to be a TA. He actually is an undergrad in Greece in the National Technical University in Athens. He was on the Greek IOI team. And then if you can see the guy in the middle in the back row, the white guy, so there's only a few white guys in this picture. His name is Artem. He's actually an undergrad in Russia, in Moscow, and he's active on Code Forces. His username is I'm forgetting what his username is. But yeah, so we have people kind of from all over the place, and we've had TAs from Iran, from India, from England, from the U.S., Canada, etc. More pictures of students in the program. These are some cities where the students came from. So you can see these 5 girls came from these 5 cities. They had an excursion to Ethiopian Airlines, and they met with the software engineering team there to learn about what it means to have a career as a software engineer in Ethiopia. These are more students, field trip. Okay, so here are 4 girls from the program. Can anyone guess, what are these girls doing on the board? Any guesses?
Come on, you should get it. Right. Okay.
Maybe don't
One
tell
guess
me
is
now, maybe,
DP. Yeah, it's
this is
written.
exactly DP. They're doing dynamic programming on the board, right? So this is the DP table that they're filling out and basically tracing back to reconstruct what the optimal solution was, right? So again, pretty much none of the students came into the program knowing how to write a single line of code, and within a couple of weeks, people are doing dynamic programming. Okay, so it was very exciting to me to see everybody getting, learning all this stuff. And here's one of the girls from the program. She's actually from a rural town, from a farming village. And this is, basically this is the week we were studying recursion. So she's just writing down some recursive solution in Python. This is merge sort, real life merge sort, okay, sorting by height. And actually the guy in the front with the black jacket, he's a rising senior at MIT. He's from a smaller town. He did the program in 2016. Now he's at MIT as an undergrad, and he's actually this summer interning at Facebook. But with COVID, he's not actually in the Bay. He's doing it remotely from his laptop. Right. So, these are teaching staff just kind of traveling around Ethiopia on the weekends, seeing the sights, feeding hyenas with their bare mouths. not necessarily something I would do. I might be a little scared myself, but it's a thing. You can do it if you want. Yeah, this is a walled city, so the more TAs here. Great. So yeah, what else? Oh, Ethiopian food. I don't know. I think a lot of you are in the South Bay. I highly recommend Zenni's in San Jose, 1320 Saratoga Avenue. In my opinion, it's the best Ethiopian restaurant in the United States. But tons of Ethiopian food in Ethiopia. So anyway, that's the end. This is my email address. Feel free to contact me if you have questions, my website. And if any of you is ever interested in the summer program AddisCoder, we do pay plane ticket, etc. for TAs. But even if not, I just wanted to show you that you guys are very lucky. As I mentioned, I didn't know about algorithms when I was your age. If I only knew, then I'm sure I would have enjoyed doing what you're doing. And there are a lot of other kids who also don't know about algorithms. So spread the word, spread the knowledge that you are getting. And maybe that's it. Let me take more questions.
Yeah. Before that, I would like to say that that's a great work, Dr. Nelson. So the AddisCoder, and very inspiring. So I hope our students also can spread their knowledge to the other ones. Great work. I appreciate you.
Oh, thank you.
Yes, if you have any questions, we have a Q&A button. Please click the button and then you can ask your questions.
Wait, so there was a question. I see a question from Kashav. For dynamic connectivity, you can't trivially use union find if the queries are online, right? You can, right? You just do find and you check whether or not they're in the same component. So if someone in the stream adds the edge with deletion, oh yeah, that was my point. If there's no deletion, if it's insertion only, then it's very easy. You just use union find and it'll be v log v bits. But if there's deletion, then you can't. So you have to do something more clever. So yeah, that was the point I was trying to make. Any other questions? Okay, if there are no more questions, then that's all I have for you. Again, email me if you have any questions, and nice to meet you all.
Hey, thank you very much for giving me the guest lecture.
Oh, I see one more. Is that a question? Oh no, just saying thanks.
Okay, thanks.
Okay,
Okay, thanks.
Okay, great. Okay, bye-bye.
Yeah, thank you very much.